at home. I posted my slides on my website, math.mit.edu/tilde-ROED, and then in the talks section. And the website that I'm going to be talking about is at tori.lmfdb.xyz. So I'll put both of those links into the chat. If I can figure out how to do that. There we go. So here are the links to the slides. And here's the link to the database that I'm going to be talking about. All right, so I'm ready to go when everyone is. I don't know whether we're waiting for anybody else.
We are not. So the MIT tradition is 4:35. So it's, I believe, 4:35. So that would be wonderful.
Sounds good. So I'm going to be talking about project in progress to build a database of tori over p-adic fields, and show you kind of an early version of that database that's still missing a lot of functionality, and talk about some of the kind of techniques that I'm thinking about using to do so. So an algebraic torus for me is going to be a group scheme isomorphic to some power of this split multiplicative group after base change to the algebraic closure. And of course, over an algebraically closed field, these tori are pretty boring. There's one in each dimension. It's when you introduce the Gaura action and start thinking about tori over non-algebraically closed fields that you get a lot of interesting behavior. So what I would like to do is to explicitly compute a list of all kind of isomorphism classes of algebraic tori over QP for the dimension up to some bound. And I'll explain why why I don't really need to restrict the P a little bit later. What's the general approach for doing this? We have a functor from tori to lattices with an action of a Gaura group given by the character lattice. So if I have a torus, then I can look at characters from that torus into GM. And those characters, these are just HOMs over K bar, and this set of homomorphisms has an action of the Gaura group.
Sorry, so is this restricted to characteristic 0?
No, I don't think this theorem is restricted to characteristic 0. I'll be restricting to characteristic 0 a little later, mainly because I want there to be finitely many fields, and in characteristic P, the absolute Gaura group is not finitely generated, and there are just lots and lots of field extensions. But this theorem is true in characteristic P as well. Okay, so that's the general sketch. We're looking for these tori. We're going to think about them in terms of representations of the absolute Gaura group on z to the n. And in there, the dimension of that lattice is going to be the same as the dimension of our torus that we get. So let me say what happens over R, because over R, the story is very simple. And so these examples will kind of be nice to think about. So there are only 3 tori that you need to think about over R. So the first is the split torus. So the one-dimensional torus with R points equal to R cross. The second is the Weil restriction of scalars from C of the split torus over C. So this is now a 2-dimensional torus over the real numbers, and its R points are C cross. And the third is that's a 2-dimensional torus, and it has a one-dimensional subtorus sitting inside it, namely the norm 1 elements. So those elements of C cross where ZZ bar is equal to 1. This is a process you can do more generally whenever you have a field extension. You can take the restriction of scalars of the split torus and then look at the norm 1 subtorus, which will be a codimension 1 subtorus. And the theorem then is that every algebraic torus over the reals is a product of these tori. So this is a statement about kind of groups of order 2 inside up to conjugacy inside GL and Z. So what about over QP? So what's our approach going to be? We're looking for actions of the Gaura group on some lattice Z to the n. Since our action is continuous, by the definition of a continuous action, it's going to factor through some finite quotient. So there'll be some finite degree splitting field L, Gaura, so that the map from the action from the absolute Gaura group factors through that finite quotient. And a faithful action of G on Z to the n, that's the same as an embedding of G into GL and Z. So we can break up the task of finding all these tori into 3 parts. So for each dimension, we can first list all of the finite subgroups of GL and Z up to conjugacy. So up to conjugacy is going to translate into being up to isomorphism on the torus side. And for fixed in, the set of such subgroups is finite up to conjugacy. For each pair of G and P, we can try to list all Gaura extensions of QP whose Gaura group is isomorphic to G. So this is some sort of explicit version of the inverse Gaura problem. So given a finite, given a Gaura group, produce the fields with that Gaura group. Again, for fixed G and P, the set of L is finite. And when P doesn't divide the order of G, then these extensions are what are called tame. And so we understand them pretty well. We can write down what they look like. And for each, finally, for each G, I'll show you, we'll see on the next slide that the first 2 points don't actually give us a full description of a torus. So we need to compute the automorphisms of G up to GL and Z conjugacy. So I'm going to refer to that pair of G and L as a proto-torus, kind of the first part of the data that we need for a torus. And so what we've produced via this process is a pair of a subgroup and kind of some field that gives us the right Gaura group. And the difference between a conjugacy class of embeddings and a conjugacy class of subgroups is measured by the quotient of what all automorphisms of G are compared with the automorphisms that we can get by conjugating within GL and Z. So if we look at the normalizer of our subgroup G inside GL and Z modulo the centralizer, that tells us the automorphisms that we can get by conjugating by matrices. And then that may not be the full automorphism group. And if not, then we can get additional embeddings by precomposing with automorphisms of G. So I'm going to refer to the size of this quotient, A mod W, as the ambiguity of G. And so given a prototorus, G and L, given a group and a field, they're going to be A corresponding isomorphism classes of tori, each with splitting field equal to L. So here's an example. Let's look at inside GL3Z. We have a subgroup generated by these 2 matrices. These 2 matrices commute, both have order 2. So the subgroup is isomorphic to the group of order 4 C2 squared. And the normalizer and centralizer of this subgroup are both obtained by just throwing in minus the identity. And so that means that W is trivial. You can't get any automorphisms of this group by conjugating my matrices. But the automorphism group of C2 squared is S3. And so there are going to need to be 6 tori that correspond to this subgroup. And if P is odd, then we can easily write down what the field extension is that has this as its Gaura group or a field extension that has this as its Gaura group. So you can take the compositum of the 3 quadratic extensions of QP, and for each labeling of those 3 extensions, you get a different torus. So you can think about sigma I being the non-trivial element that fixes each of these 3 quadratic subfields, and then you can map sigma I to AI, to alpha I, each of these matrices, and that gives you a specific embedding of this, of your Gaura group into GL3Z, and then you can compute what the fixed points of this are. And so the torus over QP is going to be this norm 1 torus for L1 cross the restriction of scalars torus for L2. It's a 3-dimensional torus. And clearly these are distinct as you vary over the different labelings of these 3 quadratic fields. Just going to mention briefly that you can do the same story again for tori-apt to isogeny. So we've been talking about tori-apt to isomorphism. If you want to look at isogenies, that corresponds to, instead of taking GL in Z conjugacy, you can look at which subgroups become conjugate under the action of GL in Q. And you can just modify the story by changing W to some W prime, which measures the normalizer modulo the centralizer in GL in Q. And now you get the same kind of thing. You get G prime measured up to GL in Q conjugacy together with a field extension with the right Gaura group, and then you get a number of isogeny classes of tori kind of given by this quotient A prime. As an example of isogeny, we have, in our real case, we have GM cross U, that's a 2-dimensional torus, and S, those are isogynous but not isomorphic. So GM cross U, that gives you an action. GM is 1-dimensional torus where the complex conjugation acts trivially. U is 1-dimensional torus where complex conjugation acts by -1. And so the product torus is a diagonal, corresponds to a diagonal matrix where complex conjugation acts by 1, 0, 0, -1. And then S, complex conjugation acts by 0, 1, 1, 0. These are conjugate inside GL2Q, but not inside GL2Z. All right, so there are 3 parts of this problem now. There's the kind of finding the groups, finding the fields, and then kind of computing the ambiguity and kind of computing additional data we want to about this torus, about each torus. So I'm going to first talk about a little bit about what this inverse Gallop problem looks like. So this is the problem of finding field extensions of QP that have the right Gallop group. So the problem is, given G, we can break this up into kind of 3 progressively more difficult problems. So first, do there exist fields with that Gaura group? So this is the classic inverse Gaura problem over Q. Like, does there exist a field extension of Q with any given finite Gaura group? Second, you can ask for a count. So this is not something which really has an analog over Q. Over QP, there are going to be finitely many field isomorphism types of fields with a given Gaura group, and so you can ask to count them. And then finally, you can ask to enumerate them and, for example, give a defining polynomial for that field extension. So I'm going to talk mostly about 1 and 2 in this section. The enumeration problem I'm still working on. We have some data for small primes and degrees, but it's not as much as I would like. So I will hope to improve that later. So in order to talk about what extensions of p-adic fields look like, we use class field theory. So here's the summary of what class field theory tells us, kind of that's relevant for our purposes. So if you have an extension of p-adic fields and a uniformizer of the top field, you can look at a filtration on the Gaura group of, let's say it's a Gaura extension. You set GI to be those elements so that when you take, when you apply sigma to some element of your field, then the valuation is always at least I. The valuation of the difference between sigma of x and x. So the identity, for example, would have this is contained inside every GI, but any non-identity element is going to move some element of the field, and so there's going to be some value of I where it's not contained. So this gives you a filtration as I increases, starting from G minus 1, which is the same as the whole group, up through G infinity, which is the identity. You get a descending filtration. And there's a corresponding filtration on the field theory side. You can take the units in OL, and then you can take the things that are congruent to 1 modulo pi to the I. And the proposition is that there's a map given by taking sigma in some GI and mapping it to sigma of pi over pi. And this induces a well-defined map from GI mod GI plus 1 to UI mod UI plus 1. And the result that we need is that it's injective and it's independent of the uniformizer. So in particular, when I is bigger than 0, these UI mod UI plus 1s are p groups because they're that quotient is isomorphic to the isomorphic to the residue field. And so the first few pieces of the filtration we can analyze separately. The G mod G0, that's going to be cyclic, kind of generated by Frobenius. G0 mod G1 is cyclic of order prime to p. That's kind of mapping into OL cross, or the units in the residue field. And then GI mod GI plus 1 for I bigger than or equal to 1 is an elementary abelian p group. And the dimension of that is bounded by the dimension of the residue field. So this gives us a constraint on what possible groups can arise. So if we're looking for p-adic tori, we only need to analyze subgroups of GL and Z that can possibly be the Gallop group of a p-adic field. So I'm going to define a group to be potentially p-realizable if it has a filtration that looks like it could come from a ramification filtration. So what does that mean? That means that I'm just going to take 2 steps in my filtration. I'm not going to try to figure out exactly where the ramification breaks are. I'm just going to say we have 2 pieces, G0 and G1. Both of them need to be normal in G. And the quotient G mod G0 is cyclic. The quotient G0 mod G1 is cyclic. And we know a bit more. We know what the action of conjugation of that of Frobenius looks like on a generator of tame inertia. Namely, it should raise things to the pth power. So we need that some generator, sigma and tau, have the property that tau to the sigma is tau to the p. And then I'm just going to say that G1 is a p group, because any p group has a filtration where the successive quotients are z mod p's. So such a group satisfies the constraints that come from local class field theory, but it may or may not actually be the Gallop group of a p-adic field extension. So I'm going to say it's p-realizable if there's some actual field over QP so that the Gallop group of L over QP is isomorphic to G. And for those things that are not realizable, I'm going to say it's minimally unrealizable if it's not realizable, but every proper quotient is. So it turns out that if you look at, I'll get to that in a second. So here's an example. So this is the largest subgroup of GL4Z. It's the Weil group of F4. It's generated by these 2 explicit matrices, has order 1152. And this group is not p-realizable for any p. And the reason is that if p doesn't divide the order of the group, then you don't get any contribution from this G1 part. And then the whole group has to be obtained by these 2 cyclic pieces glued together. So what you need is that your group is metacyclic. Has some cyclic subgroup, which is normal, where the quotient is cyclic as well. And this group W of F4 doesn't have that property. And then you can similarly say, look at p equals 2 and p equals 3, and take the quotient by the biggest thing that G1 could be. Well, we know that G1 is supposed to be normal, and we know it's supposed to be a p group. So the p core for a given prime p is the largest normal p subgroup. So here, when p is 2, you can take that quotient by the largest normal 2 subgroup, and you get S3 squared. And that's not metacyclic. And for p equals 3, the p core is trivial. There's nothing at all. And so that tells you that this can't be a p-adic Gallop group. Here are some examples of the of minimally unrealizable groups. I'm here taking the case where the Frattini subgroup, sorry, V is the p-core. I'm going to look at the case where V is abelian for simplicity. So some of them are pretty small. So F3 cubed can't be the Gallop group of a extension of Q3. But then there's some other ones. So I have, I'm going to not linger on this too much, but I've thought a little bit about what kinds of Gallop groups can arise. And I have a reasonable algorithm that works for small groups to tell how many groups there are. I'll also say that we have a criterion. If your group is actually a p group, then we can easily determine whether or not it is a Gaura extension. It is the Gaura group of an extension of QP. And how do you do that? Well, let's let W be the Frattini subgroup. So that's the product of the p powers of G with the commutator of G. So W is the quotient, G mod W is the maximal elementary abelian quotient of G. And a set of elements of G generates G if and only if its projection onto G mod W spans G mod W as an FP vector space. And so the result is that when P is bigger than 2, G will be a P group if and only if, and G is a P group, so the order of G is a power of P. Then G is P realizable if and only if the dimension of this quotient G mod W is less than 3. So for P groups, we fully understand what's going on in terms of realizability. There's still a question of counting field extensions and writing them down, and that's not easy. So one of the reasons I got interested in this counting problem was the question of whether or not this computational question is feasible. So if there are just too many field extensions, then you don't want to write them all down. And one way that you could try to kind of first approach guessing how many extensions there are is to look at this previous result. I told you this in terms of realizability, but the counting problem is actually not so bad. Sorry, I said the counting problem was harder. It's not so hard when it's a P group. And so when you have something that's not a P group, you could say, well, let's take the part that's that could be the unramified part and take an extension of that, and then look at how many extensions of that maximal unramified subextension there are. And the result that you get is that there are lots and lots and lots of these, so billions of possible fields. And the problem is that most of those fields are not Galois over QP. And so they can't be the group G. So I wanted to count how many extensions there were with a given G. So here are the results. So what do these tables show you? So for each prime P, I'm showing you how many groups G there are that are potentially P realizable, and where the count of fields is at least n. So that tallest bar on the left, that measures the total number of potentially P realizable G. And then the drop from there from n equals 0 to n equals 1, that difference are the things that are not P realizable. And then the drop from n equals 1 to n equals 2 are the things that are P realizable uniquely. So there's a unique Gaua extension with that Gaua group. And then you can see it goes down. So most groups that arise in not too many ways. There are not too many field extensions. And the counts that show up, so I only went up to 24. The counts that show up that are the largest come from cyclic groups. And there are only several thousand. This is for G up to size 2000. So G that show up in the small groups database. And I'm doing this only for odd P. essentially because my methods rely on a description of the absolute Gaura group of QP that's not available for p equals 2. All right, so this analysis suggests that we can have a hope of listing all field extensions with a given Gaura group for groups that show up inside GLNZ. I mean, also remember that these giant cyclic groups, these are not going to show up inside GLN because you don't have elements of order that large. So I'm hoping to add this to the L functions and modular forms database. So this is a database in number theory and arithmetic geometry that includes a bunch of objects of interest. And a lot of development is happening on it at MIT, as well as some other institutions. So what does it contain? It contains databases of global and local number fields. So the local number fields part is of great interest to us. It contains modular forms, various kinds of algebraic varieties of arithmetic interest. It includes Gaura groups. So the Gaura groups are going to be relevant for us. Sato-Tate groups, L functions of these objects. And one of the things that we're working on at the moment is improving the group theory, having tables of small groups and tables of matrix groups. So groups of subgroups, tables of subgroups of GLNZ. So what do we have already that can go into this database of tori? So we have tables of local fields produced by John Jones and David Roberts, and they're included in the LMFDB. And they're organized in a slightly different way. So they are tables of not necessarily Galois fields, where the degree of the field is small. So one way to think about that is that it's a transitive permutation representation of your Gaura group, where the degree of the permutation representation is bounded by 15. So for the groups that show up for us, some of them will lie inside this field, but others will not. Even if you go up through tori of dimension 4, there are examples where the minimal permutation degree of that Gaura group is larger than 15. So we need to extend these tables. And we've got a meeting at AIM, which may or may not happen in late May, to work on this, to work on improving tables of local fields. It's also kind of coming from a slightly different perspective. We're interested in the Gaura fields. And in order to think about the Gaura closures, you need to know for any given pair of fields whether or not they have the same Gaura closure. So I'm going to think about that as kind of information about siblings. So these are two fields that have the same closure. And the tables of number fields have pretty good information about this. The tables of local fields are missing that. So we need to add that a little bit. The other thing is that we want to think about matrix representations of these Gaura groups. And so we would like to understand not just where the ramification breaks are, but what the subgroups are, so that we can think about kind of the subgroups in terms of their action on the lattice. And that's important for thinking about various representation theoretic quantities coming from that character lattice. So that's the status on the local field side. We have some data. It's not quite what we need, so we're working on improving it in a way that will make it more usable for this project. What about the subgroup side? So on the subgroup side, the answer is pretty good. So there's existing work done that gives us all subgroups of GLNZ up to conjugacy for n up to 6. So that's further than we can push the field theory side. So I haven't been really working on this part of the project much. And moreover, we have additional data for n up to 31. The number of subgroups gets to be unmanageable. So what you instead look at is the maximal irreducible ones. And so then you can try to imagine, well, we want not just the irreducible ones, but the indecomposable ones. And we don't want just the maximal ones, but we instead want the things that are potentially p-realizable. And so you can imagine pushing that n equals 6 a little further and restricting to kind of groups that could be of interest for p-adic Gallop groups. All right, so I'm going to switch to a quick demo of what's available right now in the LMFDB. So this is on a kind of alpha version of the LMFDB. So you can't go to the actual LMFDB, but it's maximize this. You can browse algebraic tori by dimension, by prime, by the degree of the splitting field. So the largest splitting field here has degree 384. I've added data just for tori up through dimension 4. You can get a random torus, and you can search for tori with a particular splitting field. So maybe let's look at the list of tori where the splitting field is 6T11. So that's a Gaura group of order 48. It's isomorphic to C2 cross S4. It's some Gaura group that can arise as the Gaura group of, well, apparently it can arise for p equals 2. Maybe it can arise for, maybe it can arise for p equals 3. Nope, it can't arise for p equals 3. So that means that these particular Gaura groups are going to only show up over Q2. So we have a bunch of examples of tori over Q2. So let's look at one of them. So this is a 3-dimensional torus over Q2. It has information about what that splitting field is. So the splitting field is the Gaura closure of the extension of Q2 defined by this degree 6 polynomial. You get information on the ramification and the discriminant of that polynomial, of that field extension. You get information on the Gaura group and the inertia degree. And here's what the character lattice looks like. So you get a free abelian group of rank 3 with an action of this absolute Gaura group factoring through a matrix group with these generators. So there's lots more that we would like to have on this site, and I'll talk a little bit more about what my wish list is for data you could include for these tori. In the meantime, I'm going to go back to the slides. You guys should feel free to keep playing around with the website if you like. So I talked a little bit about how tractable things are on the field theory side, how many extensions there are for the groups of interest to us, and we saw that that was pretty reasonable. What about on the group theory side? How many subgroups of GLNZ are there? And here's a table going up through dimension 6, which is where we have full data that shows you how big this problem is. So up through dimension 6, it looks like we're getting about a multiple of 10 every time. So every additional dimension, we get 10 times as many groups. Most of those can show up as the Gaura group of some local field. In fact, most of them are showing up as Gaura groups of 2-adic fields. Part of that is just that lots of groups are 2 groups. And if you look at groups for p bigger than 2, it drops a lot. You can also see that the problem is a lot worse, a lot more complicated than it is over the real. Over the reals in dimension 6, we only have 16 tori, whereas over Q2 there's at least 65,000 tori. Sorry, I shouldn't say at least, but it's definitely true. Remember, these are measuring subgroups, which are not in one-to-one correspondence with tori. So each of these subgroups are going to correspond. You're going to have a bunch of fields that might have that Gaura group. Of course, some of them might have 0. There may be no fields with that Gaura group, but a lot of them will have multiple fields with the same Gaura group. And then remember, we also had this notion of ambiguity where we had multiple automorphisms that we could precompose with that gave different tori.
Sorry, David, the second row here, I guess, corresponds to cyclic subgroups of GLNZ.
Exactly.
Could you explain what those numbers are?
Yeah, so this is just a count of GLNZ conjugacy classes of cyclic subgroups. So there's a particular easy kind of field extension for QP, which is the unramified field extension. There's a unique field extension of each degree. And so if you fix a subgroup of GLNZ that's cyclic, there's going to be I guess there may be ambiguity in terms of the automorphisms, whether or not you can produce the automorphisms coming from Z mod M cross via conjugation within GLNZ. But there's going to be, this is counting the number of cyclic subgroups. And so there's either that many unramified tori or slightly more unramified tori coming from ambiguity.
So how do you count the cyclic subgroup?
This is just, I don't have a formula, though there may be one. This is just using the database of subgroups. So there's, people have computed what all the subgroups are, and you can list, you can go through them and you can ask which ones are cyclic. And this is the result. So I don't have a theoretical explanation here, though there might be one. Any other questions about the table here? All right. The next question is how big these get. So if we're interested in computing field extensions, those field extensions get much harder to deal with as the size of the field gets larger. So one piece of good news for us is that the really big groups turn out to not be potentially p-adic. They're mostly non-solvable, and so therefore they can't have a filtration of the kind that we need. So I've listed the second from the bottom is the kind of the largest irreducible subgroup, and the kind of these are the Weil groups that you see on the bottom row, and these turn out to, after dimension 3, not show up for p-adic fields. And so you can see that the worst cases again are for p equals 2, where up through dimension 6 we get field extensions of degree up to 2304. And you can try to think about this in a different measure. For each of these groups, you can look for what the smallest degree permutation representation is, and try to see, all right, if I'm looking for this field as a Galois closure of some other field, what degree do I need to go up to? And there, that degree is pretty big. So some of these fields, even up through dimension 6, the degree of the permutation representation, the smallest permutation representation is degree 144 in some examples. So we don't really want to take the approach that Jones and Roberts have been taking of just classify all fields, because we're very, very far from being able to do that up through degree 144. So instead, we need to have something which is more tailored to a particular Galois group. I give you a Galois group, and you produce a field extension with that Galois group. And then I've listed a little bit kind of how this size of maximal irreducible subgroup grows. I don't know how the kind of size of the potentially p-adic subgroup grows, but it seems to be significantly better, right? If you look at the p equals 2 case, 4 to 5 to 6, we were only doubling each time. Though there do seem to be places where you get jumps, probably where you get to kind of other multiples of 2, or things with kind of large, other multiples of p, or things with large powers of p in them. So for p equals 3, we got a big jump from going from 5 to 6. For p equals 2, we got a big jump going from 3 to 4. So if you look at up through dimension 8, then the 2-adic problem will likely be pretty tough. All right, so here's a wish list. These are not things I've computed. Some of them are easy, some of them are hard. I don't know how to do them. But these are the kinds of things that I would like to have as part of an online database. So some easy things, the QP rank, so that's just the rank of the lattice that's fixed under the action of Gaura group. Some Boolean quantities, whether you're unramified, tame, anisotropic, split, induced from some field extension, what the dual torus is. Some representation theory, Arden and Swan conductors. There's an alternate perspective on tori that's pretty convenient sometimes as units in Ital algebras. So when we think about kind of the points of a torus, we can think about them in this other way. And so different perspective there. From the point of view of p-adic representation theory, one of the reasons that I've been interested in this is that you want to construct representations by taking representations over finite quotients and then pulling them back. So, and then compactly inducing them to some whole group that your torus sits inside. So to do that, we need a description of the QP points of T and of the Moy-Prasad filtration, what the successive quotients look like. Another interesting question is about neuron models. So tori are commutative groups, and when they're anisotropic, they have kind of a classical finite type neuron model. If they're even in general, they have something called a locally finite type neuron model. So this is a model over ZP that is analogous to things that you would run into for abelian varieties. And one of the things that I don't understand very well is how neuron models behave under wild base change. And so a database of kind of tori with their neuron models, information on their models might help understand that. One of the reasons we want to think about these tori is that they help us produce representations of reductive groups. And so we want to look at what are the possible embeddings of each of these tori into different reductive groups of interest. So starting with the classical groups and the kind of basic exceptional groups. There's each of these tori has a Bruhat-Titz building, and so you can ask for the fixed set of actions of the torus, or actions of kind of filtrations of the Moy-Prasad filtration. You can look at Tate cohomology groups. So there's Thomas Ruud is a grad student at UBC, has been working on this some. There's various other kind of things you can do in terms of resolutions of your torus that kind of say how far are you from being an induced torus, and what's the difference between you and an induced torus that you embed inside, etc. Here's another question that's arisen for me as I think about this. So if I take a Gaura extension of fields, I'm going to define a stem field for that extension to be some sub-extension C, so that L is the Gaura closure of C. And when you're working with number fields, it turns out that it's really good to try to work whenever possible with C and not with L. And the reason is that the degree of C over K can be exponentially smaller than the degree of L over K. For example, in the number field setting, if the Gaura group of L over K is Sn, then you can find C over K with degree n, but L over K has degree n factorial. So one thing that we'd like to do, a lot of the literature on algebraic tori kind of phrases things in terms of the action of the Gaura group. For example, the K points of the torus are given by the co-character lattice tensored with L cross fixed by the action of the Gaura group. And I don't want to do that if my degree of my Gaura group is huge. So can we compute this directly from some stem field C, along with maybe knowledge of how the Gaura group of L over C embeds inside the Gaura group of L over K? What are some applications of this kind of database? Again, this is hypothetical at the moment. So Julie Kim proved that on certain regimes of P, Jukang Yu's construction of supracuspidal representations was exhaustive, but that's not known for small characteristic. So more recently, I think Jessica Finson gave a talk this past fall about extending that to smaller P, so P that were larger than the largest prime dividing the Weil group, I think. But in small characteristic, I think it's not even expected that this list of supracuspidal representations is exhaustive. So having tori that are wild may be useful for trying to construct representations that don't show up in this list. I already mentioned the behavior neuron models under wild base change. Another question that I think would be interesting to look at is what are maximal tori in exceptional groups? So tame tori in exceptional groups have been studied by Reader, but wild tori in exceptional groups are only going to show up in small characteristic in dimension, right? The dimension is going to be bounded by the rank of your exceptional group, so it's going up to 8. The only primes we're going to be interested in are the primes dividing the order of the group, and those primes are very small. So up through dimension 6, where I have complete data, the only primes that show up are primes up to 13, 11 or 13. I think for 7 or 8, those might go up a little bit, but not by much. So the groups that show up are pretty smooth. And so building a database of tori, you can imagine saying these are all of the tori that live inside E8 for any particular QP. Finally, I want to talk about we've been using this perspective of an integral Gaura representation to think about tori, but you can also think about those integral Gaura representations on their own. So if you think about these maps from the absolute Gaura group into GLNZ, I've been focusing on QP, but you can also do this over number fields. And you get connections with various other things that arise. So here are some examples of places where you would get integral Gaura representations. So if you have a number field, then OK cross is a finitely generated abelian group. And the torsion-free quotient will then give you an integral Gaura representation of the Gaura group of K over Q. And so thinking about this kind of database as being able to provide information about those representations is another possible application. If you have an elliptic curve over a number field, then E of K is a finitely generated abelian group. And again, the torsion-free quotient will give you an integral Gaura representation. All right, so that's it. Any questions?
So if you fix a reductive group and you want to look at just tori that can appear as maximal tori in that reductive group,
yep,
then I guess more or less the Galois group has to be a subgroup of something slightly larger than the Weil group.
Yeah, exactly.
So have you, I mean, for example, in the Weil group of E8, you can ask what are the possible p-adic Galois groups inside that? Do you know what they are?
I don't, but that's been on my to-do list. I've been kind of focusing on the field theory side of things more, but yeah, that's one of the things I'd like to do, definitely. I think in this case of a split group, it's literally just kind of coming from subgroups of the Weil group. More generally, you need to take the semi-direct product with that splitting field of your reductive group.
Hi, may I ask a question?
Yeah.
It's kind of general question. Is the parallel with the theory for abelian varieties? I understand the abelian varieties case is more difficult, but in terms of the picture and methods, are they parallel to some extent?
You mean for neural models or for more general for the classification?
Well, for classification, yes, I guess.
So I think though for classification, I think they're very different. So for abelian varieties over number fields, I think the main methods that we have are modular. So you look for modular forms of various kinds, and then you try to you produce abelian varieties by kind of theorems about them corresponding to those modular forms. Over finite fields, we have additional methods, but
well, I guess the question that has a chance to be parallel is if I fix an abelian variety of the algebraic closure and I look for various forms.
I see, for forms of that. Yeah, I haven't thought about that. Okay. That's an interesting question.
Okay, thanks.
David, I think you're muted.
You can press your space bar to unmute your microphone for a moment if you have a question. We need to find a way to applaud. I don't know what the best way, well, I guess you would need to unmute permanently because it's difficult to hold the space bar down and applaud at the same time. Oh, that's right. That's right. Thank you very much, David. I appreciate this. I will post the video of the talk on the Lee Group seminar website with a link to your slides and the link to the database. This was wonderful. I'm delighted. Thank you very much.
You're welcome. Stay healthy, everyone, and enjoy the spring weather, which will be coming soon.
Thank you.